Okay, welcome back. Now I'm going to illustrate to you a demonstration that's called the model eye. It's used to show what causes nearsightedness, farsightedness, and astigmatism. So it's kind of similar to the demo that I showed you before with lenses, and then I put a magnet on a whiteboard, and then I showed you what causes nearsightedness, farsightedness with lens. The only difference is that with this, we have an actual model of an eye, and we put water in it to simulate the fluid in the eye, and then we do similar types of experiments with this. We have different kinds of lenses that we use. This one has a focal length, it's a diopters positive 20. So this one, the diopters is going to be positive 20. This will model the actual cornea of your eye, and that's the focal length of the lens. So we put it inside of the eye, video of it. The other lenses that we have with a positive focal length are positive 7 and positive 2. This will help people that are farsighted. They have to wear converging lenses. So they're positive 7 and positive 2. Right? And then we can try, depending on the farsightedness of the person, we can try which one is helping them better. The numbers that are given here are the diopters. And diopters is defined as 100 over the focal length. So depending on what the focal length of the lens is, if it's, let's say, the focal length of the lens is a positive 20 centimeters, then the diopters is going to be 100 over 20, which is going to be 5. You see, and then that's the number that's shown here. It's the ratio of 100 divided by the focal length of the lens. So the smaller the focal length, the stronger the lens is. That means the diopter reading is stronger. So that means this one, diopter reading, is the strongest lens, and it will go inside of the water to model your eye. And then this is the second strongest, and then this is the weakest. That means it doesn't have much of a curvature. The other two lenses that they've given us are negative. This one has a negative diopters, negative 1.75. So they've given us one of those. Diopters is going to be negative 1.75, right? And then they've given us another one with a negative diopter, but this is a cylindrical lens. It's a different kind of curvature. So this is a negative 5.50, and it's a cylindrical lens. That means its curvature in one direction is different than the curvature in the other direction. It models for us what the astigmatism is, what the issue of astigmatism. The other thing that they put in here is just basically a dark screen with a hole in it, and this shows you why squinting sometimes actually allows people that can't see well, because it limits the amount of light that's coming in, and it limits the diffraction of the light. So if you squint, you get a better, sharper image. So this one will also illustrate that. So this is my model eye. You can see I have here water, right? And I have a source of light here that has an arrow over it. So when it makes an image in the back of the retina, the image should be inverted. So I put this at a certain convenient distance from your eye. Now inside this spot are different placeholders, and I can put the focal length positive 20, the one with the diopter positive 20, the strongest lens. And this one I'm going to actually put inside of the water. There, and then we should be getting a sharp image here. So this is how a regular eye works, is that you get a sharp image of the light, but it's inverted, and then your brain inverts it again and makes an upright image of the source, and then this is the retina, right? So now let's model farsightedness. A person that's seeing far, what is their issue? Well, their issue is that after a while this lens gets weak and becomes less and less fat, and it's not able to give a sharp image. One of the ways we can model this is by bringing the retina closer. In the actual human, that's not actually what happens. It's just that the lens gets weaker, and the image does not focus well on the retina, and it focuses behind the retina. So to model this problem with this setup, we just take this out, and we put it at a closer notch. Okay, so you can see the different notches that's here. This one is the closest one, then the middle one, and then the back one. The back one is going to illustrate nearsightedness. I'm going to bring the retina farther out. Then the middle one is for the normal eye, and then the close one will simulate farsightedness. Okay, so then let's turn off the light. You can see that the image now is no longer sharp, it's fuzzy. What's happening is that the image is getting focused behind the retina, and so by the time it's hitting the retina, it's not focused yet. So how can we help this person? We have to put another lens similar to the curvature of the human eye, which is positive diopter. So positive 7.0, put that one in there. Put this one in the front of the eye. Okay, so now I put the positive 7, and then inside of it is the positive 20. So we can see here, oh, that made it worse. So this person's farsightedness wasn't too severe. He did not need a positive 7. He probably needed the positive 2. Right? And then put that into here, this slot now. This is the positive 2. And we look at the image, perfect. So then we have corrected his farsightedness. Okay? Now let's simulate the nearsightedness. So then I'm going to take this retina, take it all the way out to the farthest position. Okay, so now you can see the image is also fuzzy. Why? Because since the retina is there way back, the image is being formed earlier than the retina, and so by the time it hits the retina, it's also not focused. So this happens when a person's lens is too strong. Their inside eye is too curved, and so in order to simulate that, we've moved the retina back in order to simulate an issue of nearsightedness. So what kind of lens do we have to put for this person to correct them? A negative focal length to fight against their eye, which is too strong. So we take the one that's negative here. You can tell here negative 1.75. So let's put this in this notch. Okay, we put a negative one here. Now it's fighting against their lens, and now the image should be perfect. So you see, this illustrates to you, this is water here, this illustrates to you the correction made by a negative 1.75 prescription. Okay, now let's show you how this other one helps. This one, let's say this person is missing their glasses, and they don't have any glasses or they can't find them, and the image that they're seeing is fuzzy. Let's see if putting this will just help, squinting their eye. Okay. Notice what happens is it kind of dims the light a bit, the amount of light coming in, but it does make it sharper. So I'm going to take it out now. Compare, take it out. It's fuzzy, somewhat blurry. Then I put it back in. It makes the edges of the lines sharper. So this limiting the amount of light will make it more focused and will sharpen the image. So this demonstration shows that. Okay, now let's go to the normal position of the retina and show you the issue of astigmatism. Okay, now I'm going to use this diverging lens that's negative 5.5 diopters, but the curvature is that it's kind of strange. Look, if you look at carefully, it's kind of has a groove in the middle, and then this end and this end are curved like that instead of being curved in the middle, right? So it has here, this side is out and this side is out. This is called a cylindrical lens, and people with astigmatism have this issue. So when we put this, it models what happens in people with astigmatism. So I put this negative 5.5 cylindrical lens here, and you can see what happens is it makes one of the directions of they're seeing better than the others. The other ones are fuzzy. And by just rotating this, the direction that's visible, better visible, changes. So watch this as I rotate this. Now the straight direction is sharp. And then as I rotate it, the diagonal line is sharp. And as I rotate it in the other direction, the the diagonal line going downward is now sharp. So it's either this diagonal line or this diagonal line or the straight line. So this is models what happens in people with stigmatism. So how do we correct that? Well, in order to correct it, we've got to put another glass in front of it that has the opposite curvature, right? It has the opposite curvature, so if they can see this well, it will help them see the other diagonal and then the straight one well. So we correct it by putting another lens of the opposite curvature so that they can see all the angles with the same sharpness, okay? So with this demonstration, then you can investigate the concept of nearsightedness, farsightedness. You could put different lenses of different diopters. You can see how they correct, and you can see how squinting helps to see a sharper image, okay? Thank you very much.